So, for anybody who didn't see me earlier, I'm Colin Walls. I work for Mentor Graphics. In fact, I work for Mentor Embedded, which is the embedded software division of Mentor Graphics. So, here's the agenda. I'll make a few introductory remarks, and then we'll look at different modes of failure, and eventually looking at recovery, and then concluding, by which time we'll all probably have lost the will to live, because failure is something we don't like to talk about in this world. But actually, something we do need to accept, that failure of something is almost inevitable. It's very important to accept that this is the fact. And if we consider that we're talking about software, and software is incredibly complex, let's do a comparison with the real world. The most complex machine that mankind has yet made, single machine, was the Space Shuttle Orbiter, which had well over 1 million moving parts and proved to be amazingly reliable for a machine that complex. If you think a bit is the nearest thing we have to a moving part in software, well, 1 million bits would be quite a small piece of software. What's different about software compared with mechanical machines is that if one moving part, the Space Shuttle Orbiter, for example, every flying surface had servo hydraulics controlling it, and it had how many levels of redundancy? There were 7 servos driving each surface, so it had multiple levels of redundancy if there were failures. So a certain amount of failure, and the vehicle would still perform correctly. With software, you can lose 1 bit, and your system will fail. That's the possibility. So it's amazing that software does as well as we observe in everyday life. So we need to have a look, though, at how likely is failure to occur, and what we can do if we see that failure is going to occur, and maybe how we can recover from it. This is a very pragmatic discussion. I'm going to look at practical ways of dealing with it, not theoretical stuff. So what can go wrong in an embedded system? Well, the CPU can fail, the peripherals can fail, the memory can go, and the software can crash. Maybe several of those, just to make life interesting. There's 2 kinds of testing we can do, and they are quite distinct in what we can achieve. There is startup testing, and there is background testing. So startup is literally when you switch the system on, it does some testing before it starts doing its real job. And that's important to differentiate because there are opportunities for doing things at that point which we will not have later on. That's why I differentiate between them. So let's think about CPU failure first of all. Now, if we're thinking about it from a software point of view, it's a bit difficult because although it's quite unlikely for just the CPU chip to fail, it's entirely possible. Any electronic component can fail. If it has failed totally, then from the software perspective, there's not a lot we can do, because without the CPU, we don't have any software, so it's somewhat irrelevant. It's most likely to fail on power up. If you're a software engineer, that may not be obvious to you, but in general with electronics, the most likely occurrence of failure is when the power is first applied. Just life's like that. And it would be very, very unusual for a CPU to fail partially. It could happen. You know, suddenly it forgets how to add numbers together or something. That is conceivable, but very unlikely. And I suppose it might happen if there was radiation damage to the core or something like that. But in everyday life, that's unusual. CPU failure in a multi-core design gives some opportunities. Exactly how we handle it would depend on the particular application. But broadly speaking, one core can keep an eye on other cores. So if you build this into your design, that each core is checking the integrity of the others, making sure they are responding and one of them hasn't stalled, at least you can have an idea of the integrity of your system as a whole. That's a somewhat special case, of course. So what about peripheral failures, devices around the CPU? Well, if you have total failure, that's easy to detect because the device is just not responding anymore, the address isn't there, so you probably get a trap. So make sure you include trap handlers for non-existent addresses. It's easy to forget to do that because if you write your code and you debug your code and it's fully tested, then there never will be access to non-existent memory. So why bother to include a trap handler? And the reason you might include it is if some of that memory or some of that address space suddenly stops responding. So that's something to think about. In general, for peripherals, I can't say very much because each device is different. A very common testing mode for peripherals is loopback testing. So if you have a communications interface of some kind, it may have a mode whereby you can send some data which immediately comes back at you. So you're thus testing the send and receive mechanisms to at least some degree. So Ethernet interfaces have that, for example. So it's very hard to make more general comments. Memory failure. We have a lot of memory nowadays. Embedded systems may have less than the desktop PC you have, but we do tend to have a lot of memory. And it's quite surprising, in my mind, that failure of memory is not a more common occurrence, because there's so much of it. Now, it depends on the circumstances. If it's in a nice warm, if you're maintaining the memory at an ambient temperature, you're not switching it on and off very often, you're not exposing it to radiation, the likelihood of failure is pretty small, because it would have failed almost as soon as it was produced, and it's been tested before you receive it. It's most likely to fail when you power it up. One answer there is don't power it up, keep it powered all the time, and for some applications that's actually exactly what you want to do. On power up is the time you can do comprehensive testing, because nothing else is using the memory when you first boot up the system, so that's the time to take the opportunity of testing it before you get yourself into trouble by using non-functional memory later on. There's 3 broad failure modes for memory. The memory can just not respond at all. I've covered that issue already. You can have bits which get stuck, either 1 or 0, and you can have bits where addressing one bit actually addresses others as well, so kind of crosstalk mechanism. Now, we can do tests on startup. A moving ones test is the classic one. This looks for bits which are stuck and crosstalk with quite fine resolution. You do this at startup because you're going to corrupt all of memory in the process. And you have to write some code, which is quite tricky with some CPUs, that doesn't use any memory, doesn't use any RAM anyway, and only uses registers. And we can also do a moving zeros test. A moving ones test, the idea is you clear the entire memory, then for every single bit of memory, you first of all verify that everything's 0, you set the bit under test to be a 1, then you verify that it is a 1, and you verify that all the other bits are still 0, and then you set the bit back to 0 again, and then you repeat for every single bit of the system. It takes time, but there's the one way of testing that your memory is completely working. The other kind of test you can do is a pattern test. This is looking for stuck bits and crosstalk, and you can do this in a background task. So the idea here is you go through every byte of memory, and for each byte you have to lock it. In other words, the only sort of really reliable way is turning off interrupts. There may be other ways, but interrupts, if you turn them off, nobody's going to try and access the memory while you're doing this. You simply save the contents of the byte, and you try a series of values, and I use 0, FF, then AA and 55. The logic of this is 0 is zeros, obviously. That checks that all bits will set to 0. FF checks that all bits will go to 1. Then AA and 55 are the alternate 1010 type patterns, which is checking for crosstalk in a reasonable way as possible. So you simply write the value, make sure it's okay, and then restore it, and then go around again. So if you run this in a background task, assuming that task is getting some CPU time, and if you use a time slice mechanism like Serge was talking about, you do have a guaranteed amount of time that that task could have if you have a special task looking after self-testing. A key thing about these tests, particularly the moving ones test, is it can take like forever if you have a lot of memory. But you can actually optimize the test if you know the memory architecture, because you may be able to say, well, there's no possibility of these two areas of memory interacting, so we don't need to test them together. We can test them individually, and that will speed up testing enormously. So if you know about the architecture, you can leverage that. What about software errors? Well, as a software engineer, I would assume that we don't make any errors. It's only the hardware that goes wrong, but of course that isn't true. Software bugs can lead to completely unpredictable failure. The best we can do then is debugging, I suppose. Defensive code can help deal with the unexpected. There's 2 kinds of failure modes I have in mind here. One is the corruption of data, and the other is code looping in some way. code using up CPU time that it shouldn't be doing. Data corruption. What's this all about? The answer is pointers, mainly. One of the virtues, apparently, of the Java language is it has no pointers. But that's also a degree of inflexibility, which is why most people use C or C++. As soon as you use C, you tend to use pointers, and as soon as you use pointers, you use pointers to pointers, and then you might think pointers to pointers to pointers are a good idea, and so it goes on. And there seems to be a fairly close correlation between the number of levels of indirection that you use pointers to the amount of errors that you introduce. The simplest error a pointer can have is it points nowhere. It points 0. It's a null pointer. And that will cause a trap to occur, and that's easy to catch. The more difficult one is when the pointer is pointing somewhere which is valid memory, but not where you want it to point. And that's where we have more challenges to sort it out. This can lead to corruption of memory in a fairly random fashion. An MMU might help because it might enable us to limit the range of memory currently accessible, but it won't totally solve the problem. So ultimately, there's not a lot we can do about this, but we can look at a couple of special cases, and those special cases are the use of the stack, which is the most heavily used part of the memory, and we can look at array-bound violations. If we look at stack, first of all, when you're first testing your code, when you're first developing your code, you have to allocate stack space and make sure it's big enough, which is a bit of a black art to do, and do careful testing to make sure that you are only using the amount of stack space that you have allocated. So when you're doing the debugging, you might use memory access breakpoints to make sure that you're not writing outside of the stack space. And the difficult thing to predict is an unexpected recursion depth. So if you have a recursive function, that's going to use stack every time the recursion occurs. Simple rule there, don't write recursive functions. But sometimes that's the best algorithm to use, so I can't say that with too much dogma. We can take an alternative approach at runtime, and that is to add some guard words. And we test these guard words periodically. Now, the idea here is there's our stack, which is growing through memory in that direction. And when we start out, the stack pointer is pointing at the bottom of the stack, typically. And what we'll do is we'll put a guard word either end of the stack, so we allocate an extra word in each of those two locations. And we will write a value into it, which is unlikely. Now, by being unlikely, I mean it's not 0, it's not 1, it's not FFFFF. It's probably an odd value because addresses on most CPUs are even numbers, and addresses are commonly pushed to stacks. So if you make an odd number, it's not likely to occur there. So if we choose this number totally at random, there's a 4 billion to 1 chance on a 32-bit processor of a false alarm. Pretty good odds, actually. We could also use an MMU to trap these locations, but just using the value makes sense. So the idea here is we've got the stack pointing there, we've got these guard words. We use the stack for a period of time, the stack pointer moves on, all kinds of data is written to the stack. Currently, we've filled the stack up. We haven't overflowed it yet. The stack pointer is now pointing at the top guard word, so next time we push something onto the stack, the guard word is corrupted. And it will stay corrupted until somebody writes something different to it. So the background task, which is monitoring these guard words, now has the opportunity of sounding the alarm and doing something, or at least logging the fact that this stack is about to overflow into other memory. No disaster has happened yet because the guard word has absorbed this one more word of data. But we know we have a potential problem, and that needs to be highlighted. Array bounds are very similar. You set an array to be a particular size. In C, conventionally, it's a static size. There is no built-in checking of arrays in C normally. This would be regarded as unreasonable runtime overhead by most C programmers. In C++, you could add it. You could add it by overloading the square brackets operator, for example. But anyway, pointers can point off the end of the array anytime you like. You don't have to use square brackets to access memory elements in C or C++. You could still use guard words in the same principle because the most common error is just falling off the end of an array, accessing an array element -1 by accidentally incrementing or decrementing the index, or off the end of the array in the other direction. So we could use guard words in exactly the same way as I illustrated for the stack. What about code looping? An infinite loop should never occur in your code unless you decided that it was going to do so. So if something's just looping forever, it could be a programming error, or it could be a device which is failing to respond, and the software is just sitting forever waiting for it. Well, the first thing you can do is make sure you don't do that. If a device is supposed to respond in a certain period of time, well, put in a timeout. That way you can detect that some failure has occurred. In a multi-threading environment, and this actually would encompass multi-core as well, but if you simply have a multitasking environment, it's good enough. You can have a watchdog task. And a simple way of doing that is to have an event flag appertaining to each task, and the watchdog sets the flags to 1 and then goes to sleep. And then periodically, the other tasks will set their flags to 0, somewhere in their main loop of operation. And then when the watchdog wakes up, which it will do from time to time, it checks that the flags are set to 0. And if any of them are still set to 1, it concludes that one of the other tasks has got stuck in a loop or something. So the idea is, here we have 3 tasks and a watchdog. So the watchdog task is going to write 1s into these 3 event flags, and then it will go to sleep. Then task 1 does some stuff and eventually sets its flag to 0, and task 2 does the same thing. But for some reason, task 3 is preoccupied. It's either stuck in a loop or it's just doing something it's not supposed to do, so it never gets around to setting its flag to 0. So when the watchdog task wakes up and it takes a look at these flags, it sees a 1 is still there and it sounds the alarm. What sounding the alarm means, we'll come to in a second. But that's a very simple way of doing things. And the watchdog task is tiny and takes very little time to run, of course, so it's a tiny overhead to do this. So, the system is falling about around our ears, everything has gone wrong, what can we do about it? Sometimes not a lot. It's totally system dependent. Obviously, if there is a user interface, you can tell the user something has gone wrong. So if you do have a graphical interface or something, you can pop up a message saying there has been a system failure, replace the system or whatever. Just like in your car, you have lights on the dashboard that tell you green means it's okay, red means stop the car now, you're in deep trouble, yellow means you better get this looked at. We all understand that very readily. It's a kind of user interface that makes sense, and that can apply to any kind of device outside of a vehicle. A deeply embedded system may have no options to communicate with the user. If I have a heart pacemaker and there's something going wrong with it, there's no way of popping up a dialogue to say your heart's about to stop. It's probably best to just reset and keep doing what you do. There may be the opportunity of doing something else, but we'll come to that. So how do we sound the alarm? We can do some text or graphics. We may have the opportunity of making a noise. That's always good fun, making an annoying squeaking noise or something like that. If you have network connection, you could send an email. I had a customer whose system was connected to a network, and if part of the system failed, it would simply email a particular place where somebody rather would see this message saying part of the system had failed. That's not very real-time responsive, but maybe that does the job. There may be access to the system by means of it carrying a web server or an HTTP server, and therefore you can have a user interface in that respect. Simplest user interface is some LEDs, just flashing an LED. It sounds trivial, but you have the possibility for the LED being on or off, or you can have different colors which mean things just like the dashboard of a car, and you can have flashing. It's amazing what you can do with a flashing LED. I actually think if you've got one, it's best to make it flash at a gentle rate just to show the software's alive. We call it a heartbeat. And then flash it fast to indicate you have an error. A friend of mine who was a radio amateur, she suggested that maybe we should use Morse code, and therefore we could actually flash the LED to communicate long, complex messages. But I think she needs to get out more. How many people can read Morse code beyond SOS? Well, probably not many people outside this room, and not many people in it either. But the idea of using different duty cycles to flash the LED, perhaps flash, 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 stop, means one error, whereas flash, flash, stop means something else. So you can communicate quite a lot of information with LEDs, but broadly speaking, a heartbeat versus a fast flash is as good as most people want. Resetting is sometimes the only option. If you have a deeply embedded system with no UI, the best thing you can do is just reset yourself. Maybe you log the fact you did a reset away, so when somebody does talk to you at a later point, you can tell them about it. Sometimes having the user have the option of resetting is good. There's a tendency towards not having reset buttons. My picture here shows a tiny recessed reset button, which lots of devices have. I find them rather reassuring. I always keep paper clips around just in case. Modern devices often have multi-key pressing things to make them reset. But I can never remember which key I've got to hold down while I press which other key, and it tends to drive me a little bit mad. And apart from that, they're not reliable, because they rely on something in there detecting the multi-key sequence, and that might have gone wrong. This little button press actually is a little bit more likely to work on every circumstance. So to wrap up, the first rule about self-testing is the acceptance of failure as a possibility. We live in a world where we assume everything works all the time. That's a world of fantasy. We do our best to consider all possible failure modes. I don't claim to have covered every possibility in this talk, but I've given you a flavour for the kinds of things that we should worry about. And just adding a little extra code just to monitor the system health seems only sensible to me. How you incorporate that into your system depends on the kind of system you're building, but there's usually an opportunity. And then lastly, consider the action on failure. Can you just warn somebody, or can you fix it, or are you just in deep water? So with that, I'll wrap up. If you wish to communicate with me after this event, there's my email address and the address of my blog, which I write about embedded software and other things that happen to be on my mind. I will be around for the rest of today. If you wish to chat with me, just call me at some point. I can probably take a question if we have one now. We are running a little short of time, although I brought it back reasonably onto schedule, or close